Once again, a warm welcome to all of you to the Advanced Dynamics and Control Lab, Department of Mechanical Engineering, College of Engineering, Trivandrum. This is the introductory lecture series on Ansys Mechanical APDL interface. In today's video lecture, we will see the static deflection measurement of a simple spring mass damper system. This tutorial will be extended to model as well as transient analysis. So in today's lecture, we will be modeling a simple spring mass damper system, which is a single degree of freedom system, and the mass is 1 kg, the spring stiffness is 1000 Newton per meter, and the force to be applied is just 1 Newton. You can easily compute the static deflection by performing the simple calculation F is equal to kx, from which you get the value of displacement x is equal to F by k. For our test case, we have a force of 1 Newton is to be applied and the spring stiffness is 1000 Newton per meter. You can easily compute x is equal to 1 divided by 1000, which yields you 1 mm deflection. This is the simplest example which we can perform using Ansys. Today we will proceed with the help menu in Ansys. In Ansys we have a help section. If you click on the help button and press on help topics, in the version 15 of Ansys, there is a detailed help appearing when you click the help menu. In the help menu, if you scroll down the screen, you can see a mechanical APDL verification manual, and explanation is given like demonstrates a wide range of elements and capabilities of simple straightforward problems which have classical or readily obtainable theoretical solutions. This means that Ansys is a software which has a lot of capabilities for performing static, dynamic and transient analysis. In the mechanical APDL verification manual, we can see that many problems and standard test cases are validated with data available from classical solution. In order to get more details regarding this mechanical APDL verification manual, you can click on that link. That will take you to a list of problems which have classical well-defined solutions or from published journal paper results. Today we are going to model a spring mass system. Let us find out whether we can get some details regarding the spring mass system in the Ansys APDL verification manual. Why we use this is because when people are not aware of the element types to be used, for example, I want to model a spring mass system and I'm not aware of which elements to use, you can rely on this verification manual. The only problem with beginners is that the verification manual is written in Ansys APDL code, which may be a bit difficult to understand for beginners, but for experienced users this is a gift, especially for those who are performing research. So many commands which are even not available in the help can be accessed through the verification manual APDL code. Now I'm going to just type spring and press enter button. Now you can see from the verification manual a whole list of exercises, maybe classical solutions from standard textbooks or journal papers. You can see a whole lot of spring. Now if you observe even more carefully, you can see in VM45 it's a simple problem of natural frequency of a spring mass system, and 68 is somewhat advanced, that's power spectral density response of 2 DOF spring mass system. As we come down, we can see non-linearities, 2 degree of freedom spring mass system, and we have harmonic response, and all these are available in the verification manual. I'm going to just click on the natural frequency of a simple spring mass system. Now you can see the spring mass system modeled in XY plane in 1 dimension. We have just in the y direction deflection with the mass at point 2 and point 1. The node point 1 is fixed, and this is the element, the spring, and this is the mass. If we are not aware of what really to do with spring mass system, you can read out the reference, that's W.T. Thompson, Vibration Theory and Application. It's a standard text for vibration students. And the analysis type here, the carried out is mode frequency. Anyway, we are not going to carry out that today. We are going to just carry out the static deflection, and you can see the elements. So this is the important factor. If we are not aware of what elements to be used for such an analysis, you can just see what elements this verification manual is using. Now spring damper element is called combin 14 and the structural mass element is called mass 21. Now I have to use both these. Now why I am using mass is actually, even though it's not participating in the static analysis, I am modeling a complete spring mass damper system which will be extended to harmonic, transient as well as other analysis. Now for static deflection case, we just require the spring element, but for the completeness, for the sake of completeness, we'll be taking both these elements. Now if you observe this, you can see combin 14 and with a link. If you click the link, you'll be directed to that element help. Now from the element help, we can get more information regarding the element properties. It is a spring damper element which has capability in 1D, 2D or 3D application, and it is not having any mass. You have to use a separate element for adding mass to the nodes. You can see over here it's mass 21 element, and if I want to just open it in a new tab, just right click and open the link in a new tab. Now mass 21 is a simple element which is a point mass having rotational inertias as well as translational mass. We have key options for that. You can read through the detailed help for getting more details regarding the element. One more thing I want to add is if you want to get the stiffness metrics, mass metrics as well as other details regarding the element as well as the theory and formulation behind it, you have to go to the mechanical APDL theory and reference. If I click on mechanical APDL theory reference, I will be directed to a menu where you can see a whole lot of data. In order to find out our element, just search through this document by pressing Ctrl F. Once I press Ctrl F, now I want to get more details regarding the shape function and related properties of combin 14 element. So I'm going to just type combin 14, COMBIN 14, and press enter key. Once I press the enter key, you will be automatically directed to the combin spring damper element. If I click on this link, more details regarding that element will be available, which was not previously available in the element reference. And this is what you get: the stiffness pause, the stiffness metrics, the damping, as well as the other related stress stiffening metrics and others. And the equations regarding the shape functions and all those things can be obtained by clicking over the equations over here, and you'll be directed to that shape function, which is just a simple one-dimensional shape function for a two-noded element without rotations. That is what you see. Similarly for mass element also you can get help. If you want to just come back to the previous menu, you can just click the back button, and just one more time if I click, it will be bringing back you to the mechanical reference theory reference manual. Just press Ctrl F and again type over here, you can type mass 21 and press enter button. Once you press mass 21, you will be directed to a menu. You can click on that and the link leads to you to the mass matrix formulation, which is a 6x6 matrix with 3 translational mass and 3 rotational mass and the related data. This is how we can get help regarding different element types in Ansys. This can be extended to beam, shell or other coupled elements. Now let us come back to our interface. In this interface, you can see the front screen. This is called Ansys display screen, working screen, which is black in color. You can change the screen color if you want from the plot controls. Go to style and you can change the background over here. Now I am just operating with this black background. Now on the right pane you can see viewing controls, and if you just place your mouse pointer over any icon, it will give you the explanation, the short explanation regarding the use of that icon. This is isometric view. If I click, the coordinate system is being aligned in the isometric orientation. This is the oblique orientation. We have front view, we have top, side views and all those things. And if we are zoomed out of the screen, for example, one more thing I want to add is there's an easy keyboard plus mouse combination for panning and zooming. If you have a middle mouse button, if you scroll it, you can zoom in and zoom out. If you press just the control key pressed, and if you press the left mouse button, move it, it is panning in left, right and top down direction. If you want to rotate it, you can just press on the control key and just the right mouse button and rotate. If you are just out of the screen and you cannot view your coordinate system or your object, you can just fit to the screen by clicking over here, and that will bring back you to the original initial position. It's a very useful function once you get zoomed out of the screen. So that's all about the zooming option. You have more zooming options over here. The panning, other than the mouse plus keyboard shortcut, you have the panning option over here and the rotation option over here, and that's all about your viewing controls. Now let's come back to the left pane. The left pane gives you the Ansys main menu having all the options. The basic steps in finite element are pre-processing, solution phase and post-processing. Ansys offers two post-processors. One is general post-processor and time history post-processor. General post-processor is used when we have no derivative with respect to time. If it is time independent, we usually go with general post-processor. If you have a transient analysis or a time dependent, some sort of time dependent data, you go with time history post-processor. In our analysis, since it is a static problem, it is independent of time, and hence we deal with general post-processor. Now let us go to the utility menu. This is the Ansys utility menu. You see at the top the Ansys utility menu with all its options. We have already used the help pane, and if you just go to the file tab, this is very important. Before you begin any analysis, you can create a directory previously in your drive and change that directory by clicking over here and just assigning a directory from your drive. For example, if I'm just using this Ansys drive, which I have already selected. Now if I'm going to save any file, now that will be stored in the Ansys folder, and this is very important since you can safely store your valuable data in a separate folder and it won't be overwritten by the previously or the later files which you're going to do. And that's all about the changing of directories. And Ansys is not having any undo option, so you have to save your work whenever you complete a particular stage. For example, if I complete the model, I can just save the model by clicking save as and give a name. You can just remove the star sign, and .db must be kept because it is the standard Ansys extension, and you can just save a solid model if you have just modeled and completed it. Now once you have completed the meshing and you have completed the mesh and you are going to just apply the load, if you just want to save in between, just go to save as, and with a different name you can save as a meshed model. So you can use meshed model for saving your mesh model. And similarly, you can save different stages of your analysis like this, and if some error occurs, you can resume from the previously saved state by just clicking on resume from and click on solid model and OK. When you click in such a pattern, you will restart your analysis from the solid model stage and there won't be any mesh. That's all about the saving of files. And let us now start the analysis. As we have seen from the verification manual, two elements which we'll be using today will be Compin 14, which is a spring damper element, and Mass 21, which is a three-dimensional mass element. Now let's click on preprocessor. When I click preprocessor, I have to first select the element type. I click on element type and add, delete and edit. Click on the add button. Then the first element which I'm going to select is the first structural mass. You can see Mass 21 named over here. Press OK button. The second element which I want to select is a combination. So again, I click the add button and I scroll down the screen. There will be an option like combination. So if you are not finding it, just scroll through the element list and you will land up in the combination. Yes. In combination, we have different types of elements, and as we have seen from the verification manual, for a linear static analysis, spring damper 14 will do. I click on spring damper 14 element and press OK button. Now my two elements are selected. Now I want to modify the element options. In order to modify element options, by placing your mouse on Mass 21, click on the options. When you click the options, we have so many options being displayed. 3 options are there, and the rotary inertia option I'm just going to modify. If you observe the option clearly, you can see 3D without rotational inertia, 2D with rotational inertia, 2D without rotational inertia. Since in this analysis we are not dealing with any rotations, it is just a simple translation of a spring mass system, you can go with 2D without rotational inertia and press OK button. Similarly, for the combination element also, you have the options and you can directly modify the options over here. If 3D longitudinal behavior is being changed to just 2D longitudinal behavior, and press OK button. And one more thing you have to notice, in order to get a context specific help, you can just click on this combine element, press on options. From the options of a particular element, if you're going to click the help menu, you'll be directly taken to the element specific help related to component 14 element. That's very useful, since you don't have to go through the whole process of help and searching the keyword. You can directly press the help button and you'll be automatically taken to the corresponding help file, and that is called context specific help in Ansys. Okay, if sometimes there may be some error which may result in the suppressing of the help screen, you can just restart Ansys and redo the same and you will get the screen very easily. That's all about element selection. Next step, for a discrete system like a spring mass system, or if you're inputting for a bar, a discrete some values of area or something like that, you can go with the real constants. But if you're really inputting the constitutive matrix, you have to go with the material property tab. Now for the symbol analysis, we go with the real constants, press on add button, and you have to add mass as well as the spring damper values. Now I go with mass, I just press the OK button, and my rest real constant is being the mass of that particular element, and I'm going to give 1, that is 1 kg mass. And one more thing I want to add is that Ansys is not operating with any units, so it's working like a calculator, and you must be very careful in inputting the units, because you have to be consistent with the system of units which you're going to input. Otherwise, this will lead to mismatch of units and computational errors. Press the OK button. Next step is to add another real constant, which is the value of the spring and as well as the damper. Now I give the value of just the spring for the time being. I'm not going to model any damper right now. I'm just going to model the spring. The spring constant is, as I have told before, I'm going to take as 1000 Newton per meter. Now we have the options for damping. For damper, if you're performing an analysis using a damper, you can just input your damper values, the damping values over here, damping coefficient CV1, as well as a non-linear damping coefficient you can add over here. Press OK button. Now we have completed the real constant input for both mass as well as the spring. Now we go to the modeling tab. Now for modeling a spring, you can arbitrarily create a line and mesh it with the spring element. There is no relevance to the length of the line, since it is just a 2-noded element and it is having one stiffness value 1000. So the length is immaterial, but the only thing we have to make sure that you have to mesh with a single element. We have to use a single spring. We are using just a single spring, so that must be kept in mind. First, in order to create a line, we have to create a key point. 2 key points are required to create a line. I'm just going to create a line by clicking create. First key points, then inactive coordinate system. If I'm going to give a number over here, Ansys will stop its automatic numbering scheme. Otherwise, if you're not going to use a number, Ansys will automatically start numbering from 1 and so forth. So I'm not going to disturb the numbering scheme of Ansys. Just I enter the coordinates of my points, which is the origin at first, and next is I'm just giving an arbitrary length of 1 centimeter. This is just an arbitrary length for modeling the spring. You can even model the spring by placing coincident nodes. That's also possible. 2 nodes in the same location connected by a spring is also possible, but in order to get a physical feel and to display the element, I'm using this strategy. Press OK button. Now you have 2 key points created. You can see point number 1 and point number 2. You can change the orientation by clicking over the front view, top view, etc. Now the next step is to create a line. Press the line and again a straight line. Press this point and press this point and you will get a line. And after getting the line, we have completed the solid model. Solid model is just a collection of points in space. You don't have any physical relevance to solid model. In order to convert a solid model to a finite element model, we have to mesh. Next step is meshing. Click on the mesh tool. You have a mesh tool palette. I'm going to use that mesh tool palette. Click on the mesh tool palette, and the first step is to see which element you're going to mesh. You cannot mesh two at a time. I'm going to use, in the beginning, I'm going to mesh the spring and later the mass. For that, we have to set the element attributes from the global set tab. Now automatically it is assigned as mass 21. I can just click the pane over here and change it to compin 14, which is a spring element, and I have to change the real constant to 2 and press OK. Now I am operating with the spring damper element with real constant set to 2. Now the first step is to ascertain or to make it sure that you are just using one element, one spring alone, and not two. If you're not going to specify the size, Ansys will automatically take an arbitrary number. For example, if I am not going to specify the number of elements to be used in this line, Ansys may take 2 springs. So in order to avoid that, just click on the set button and press this line and press OK. And once you press OK, the element edge length may be input, or you can input the number of divisions. So I want just one element to be used, and I'm using that as 1. Press OK button. Now you have set the element number to be 1. Now in order to mesh it, change the option to lines and press on the mesh button and select this line and press OK. Now our element is ready. How to understand that element is ready? Just go to the list option and press on nodes and OK. Now you can see 2 nodes, node number 1 and 2. In order to see the nodes, you can see the location which we have input. If you want to just see the numbering of the nodes, go to plot controls and press on numbering and switch on the node numbering to on. And now you can view the node numbers as 1 and 2. In order to switch off the numbering, again go back to the same option, just uncheck it and press OK button. And now we have the elements and nodes created. We have one spring without any mass. Now in order to view the pictorial representation of a spring, there's one option in Ansys. Go to plot controls, go to style, and go to size and shape, and just check on element shape on and press OK button. Now you can see the spring in a pictorial representation. If you want to switch it off, go to plot controls, go to style, size and shape, and uncheck. Press OK. Now you're back to the original view. The next step is to create the mass. In order to create mass, first you have to change the options to mass as well as the real constant to set number 1 and press OK. Now in order to mesh a mass, you have to mesh a key point. Now I'm just going to mesh this key point number 2 over here. Just change the option to key points. Press on the mesh button, select this key point and press OK. Now you have a mask created at point number 2. How to view this? The same procedure. Go to style, size and shape and switch on the display of element. Now you can see a spring with a mask. Again, to switch off that, go to size and shape and uncheck, and you will get a spring mask system as shown over here. The next step is the application of boundary condition. The analysis type which we are going to do today is static analysis. Click on new analysis and enable static option, which is the default option. Press OK. The next step is to define the boundary conditions. We are going to just constrain the left end and to apply a load of 1 Newton on the right hand. Press apply button, go to structural displacement and on nodes. Click on the left end and press OK. Since we have selected a 2-dimensional behavior for the spring, you can see 2 degrees of freedom. Press UX and UI and press 0. Give 0 as the input for displacement value. Even though you're not giving the 0 input, automatically Ansys will take a 0 value. Press OK, and our left end is constrained for the analysis. Next step and the final boundary condition, what we are going to give is the force. A force is to be applied as the right node. Press on force moment and press on nodes. Press the right node and press OK button. We are going to apply the force in the direction Fx, and that too in the positive direction. In order to apply a force in the positive direction of an axis, give the positive value for the force. If you want to apply in the negative sense, you can give negative value. For the positive sense, I'm just going to give 1 Newton. Press OK. Now our model is complete. The next and the final step in this finite element analysis solution phase is to press the solve button. Press current load step and OK. Now you are done with the solution. Once you're done with the solution, Ansys will give a note like solution is done. Now in order to view the deformed results, Since we are doing a static analysis, we can go with the general post processor. In the general post processor, go to plot results and deformed shape. If you want to view both deformed and undeformed shape together, just click on this option and press OK button. You can see the deformation, and the value of deformation is just 1 by 1000. It's just 1 mm. This is very simple. Anybody can calculate by just simple hand calculation. Now this is the deflected shape. If you want to view the animation, it's very easy. Go to plot controls. We can animate the deflected shape from deformed results and DOF solution and translation X. And this is the deformation. And you can increase the speed of animation by moving this pointer to the left. And this is what we see. This is the most simple analysis which can be performed using Ansys FE package. Thank you very much for listening to this lecture.